Let's solve a question from linear differential equation with constant coefficient. So the question in front of us is solve d square minus 3d plus 2 operating on y equals to hyperbolic cos of x. Now for solving this question, first of all focus on LHS, because it is LHS which will give you the complementary function. So for complementary function, first of all I need my auxiliary equation. How to find that? Replace this d by m, so m square minus 3m plus 2, and then equate it to 0. Then solve it. So m square minus 2m minus m plus 2 equals to 0. Okay, so m minus 2 minus 1 m minus 2 equals to 0. So m equals to 2 and m equals to 1. So I can easily write my complementary function as c1 e power first root into x plus c2 e power second root into x. I am done with my complementary function. Coming to the auxiliary equation, for that there is a small concept that we can write hyperbolic cos of x as my hyperbolic cos of x is e power x plus e power minus x divided by. There are two methods basically to solve this particular integral. First one is this. Replace this hyperbolic cos of x by this thing. The second method is like we used to do for cos ax and sin ax. In cos ax or sin ax, we used to replace d square by minus of a square. D is from this equation. Now in hyperbolic cos of ax or hyperbolic sine of ax, what we can do is we can replace this d square by simply a square. So these two things are there. First one is this, second one is this. Both are equally lengthy, so whichever method suits you better, you may try that. I will go with the first one because ultimately I need to convert that into e power x form. So for that, first method looks better to me. So for particular integral, I can write 1 upon f of d, which is d square minus 3d plus 2, and this is operating on hyperbolic cos of x. So 1 upon d square minus 3d plus 2. Now I can write this hyperbolic cos of x as e power x plus e power minus x divided by 2. Okay, now what I can do is I can separate this into two parts. First part being 1 upon d square minus 3d plus 2 operating on e power x plus half 1 upon d square minus 3d plus 2 operating on e power minus x. So what is the rule for e power ax? A here is 1 because e power 1 into x. So just replace all the d which is present by 1. So 1 by 2, 1 upon 1 minus 3 plus 2. Okay. So as you can see, this denominator is becoming 0. So In case denominator becomes 0, we go back. We first check whether denominator is 0 or not. If it is 0, we go back, and what we do, we multiply this by 1x, so x by 2, and differentiate this denominator. So if you differentiate, you are getting 2d minus 3. Now this operates on e power x plus. Here also you check, you will have to replace this d by minus 1 in this case. So minus 1 square is 1, 1 plus 2 is 3, and here if you put 3, so it will become minus 3 into if you put d as minus 1, so you'll get plus 3 from here, plus 3 and plus 3, 6. So no problem in this case. So 1 by 2, 1 upon 1 plus 2, 3, and plus 3, 6. Okay. And this is e power minus x. Okay. Now here, now you can put this again you can put this 1 here, so x by 2. If you put 1, you will get 2 minus 3, which is minus 1, so I can take that minus sign here. 1 upon 1 is not good to write, so let's remove that. Simply write e power x here. Second one is easily solved, 1 by 12 e power minus x. Okay, so fine. So if this is a great simplified version, so my final answer will be if I were to write, will be y equals to CF plus PI. Okay, so what was my CF? My CF was C1 e power 2x plus C2 e power x plus my PI, which is minus of x by 2 e power x plus of 1 by 12 e power minus x. So this is the answer. I hope you understood this very well, because I gone through the basic steps possible. First step was to find the auxiliary equation, then the roots, then the complementary function, you all know. Then this two approach we had, so I gone through the first approach. Write this as e power x plus e power minus x by 2, and then I solved further and got to my particular integral, and final answer is y equals to CF plus PI.